All right, guys, welcome back. We're here in Chapter 7, Sampling Distributions, and what we're going to be talking about in Section 7.1 is what is a sampling distribution, and we're going to look at some examples here and all these learning targets that we have, we will hit. So we're going to break this up into two sections. First section, here we go. So remember, as we talked about before, vocabulary, statistic is a number that describes some characteristic of a sample where the parameter is describing the population. So remember those two things, that's important. So again, we use the different symbols. X bar is the sample mean, where mu is the population mean. We use p hat as the sample proportion, and p, of course, is just the population proportion. And then notice the difference of the standard deviations, s sub x, or we can use sigma here for the population standard deviation. So remember those symbols and what they mean. All right, so remember, a sample statistic is sometimes called a point estimator of the corresponding population parameter because the estimate is a single point on a number line. All right, so let's look at a problem here. Identify the population, the parameter, the sample, and the statistic in each of the following settings. Now, a Gallup poll asked 515 randomly selected U.S. adults if they believed in ghosts, and of the respondents, 160 said yes. So let's take a look at what we have here. The population, of course, is all U.S. adults. P, the parameter, of course, is the proportion of all U.S. adults who believe in ghosts. Now, the sample is the 515 people who were interviewed, and P hat, that's the proportion. So we'd have to say 160 of the 515 asked, so that's 0.31, of course, and that's from the sample, of course. Okay, that's why it's got a P hat. All right, so let's take a look at this one. During the winter months, temperature outside the Stearns' cabin stays well below freezing, so to prevent the pipes from freezing, sets the thermostat at 50. Wants to know how low the temperature actually gets in the cabin, and a digital thermometer records the indoor temperature on 20 randomly chosen times during a given day. Minimum reading is 38 degrees. Now, the population, of course, would be all of the times during the day in the question. The parameter, of course, is the true minimum temperature in the cabin at all times that day. The sample is, of course, the 20 randomly selected times. And then the statistic, of course, would certainly be the sample minimum temperature of 38 degrees. So there we go. So just going to use those. Now, kind of AP tip, that's always good to get these. Many students lose credit on the AP statistics exam when defining parameters because their description refers to the sample instead of the population, or because the description isn't clear about which group of individuals the parameter is describing. So when defining parameter, all right, we suggest including the word all or the word true in your description to make it clear you aren't referring to the sample statistic. Because that's a good point right there. All right, now remember, S comes from sample, P comes from populations. So statistics are from samples, parameters are from populations. That's a good way to remember it. Cheesy makes it easy, right? All right, so let's talk about the idea of a sampling distribution. Now, sampling variability refers to the fact that different random samples of the same size from the same population produce different values for a statistic. And we should know that, of course. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Okay, so we're going to look at everything that possibly could happen in that. We're going to see a pretty good example of that here coming up. All right. So let's see, John and Carol have 4 grown sons. Their heights are 71, 75, 72, and 68. A, we're going to list all 6 possible samples of size 2. Okay, so we're going to do that. We're going to calculate the mean of each sample and display the sampling distribution of the sample mean using a dot plot. And we're going to calculate the range of each sample. So let's list them out here. So we could pair 71 and 75, 71 and 72, 71 and 68. We could then do 75 and 72. 75 and 78, or 68, I'm sorry, and then 72 and 68. Those are all the different combinations of choosing 2 out of that, and so there's 6 possible. So finding the mean of those, very simply, is just add the 2 up, divide by 2, so we get the means. You notice now, again, since we took a sample out of there, look at those means are different. And that's what we talk about, is that there's different even though we're taking the same size from the same population, yeah, we can get different means. And this is a dot plot showing that. Okay. All right. Now, again, if we did the sample range, All right, just take the high minus the low, yeah, and we see we have some variability in there, and there's the sample range, the distribution of those that we could have as well. All right. Now, let's take a look at this now. Determine how much homework time students will get in class. Mrs. Lynn, I'm sorry, has a student select a simple random sample of 20 chips from a large bag. Now, the number of red chips in the simple random sample determines the number of minutes in class students get to work on homework. Now, Mrs. Lynn claims that there are 200 chips in the bag and that 100 of them are red. When Jenna selected a random sample of 20 chips, she got 7 red ones. Now, does this provide convincing evidence that less than half the chips in the bag are red? Okay, so what's the evidence that less than half of the chips in the bag are red? Well, we're looking here. Hey, we got we got 7 out of 20, which is only 35%, which is less than 50. Now, could that happen? Is that reasonable to assume that there's maybe someone's not telling the truth? Well, that's something to look at, isn't it, anyway? So what are some 2 explanations? Now, a couple explanations of what happened there is that, well, is it possible that Mrs. Lynn is telling the truth and that she just had a sample proportion that is less than 50% because of variability? It's also possible that Mrs. Lynn is not telling the truth and that there are less than half the chips. So how do we know, or how can we provide a little more evidence to suggest that? Well, when using technology to simulate choosing 500 simple random samples of size 20 from a population of 20 chips where 100 are red and 100 are blue, the dot plot shows the sample proportion of red chips for each of the 500 samples. Now, there is one dot at 0.8. Well, that means that one time in this simulation, we got a sample proportion of 80%. In other words, 16 out of the 20 were the red ones we were looking for. Okay. So there's that variability. Now, again, as we kind of take a look at it, would it be surprising to get a sample of 0.35? And as we look at our chart, well, no, it's not. It's not that uncommon to have there. So there's many examples that would be 0.35 or smaller. So so I'm saying that there's not really not a real big surprise. So again, if we were to go on the previous answers, I would say that I would assume Mrs. Lynn's telling the truth and that this was just due to some variability in our sampling. So there's not really convincing evidence there. So that's kind of how we would decide that. So it's always good to use statistics to judge that. Now again, when we simulate a sampling distribution using assumed values for the parameters, like in the chips, for example, the resulting distribution, sometimes we call this a randomized distribution, is what that's sometimes referred to. All right, so again, figure 7.2, let's kind of talk about here. The idea of sampling distributions is to take many samples of the same population, collect the value of the statistic from the samples, and display the distribution of the statistic. Now, the dot plot shows the approximate sampling distribution of p hat. That's the sample proportion of red chips. So again, we can kind of see this. We start with our population distribution. Okay, so here's some different sample data that we have. We can put that into a dot plot here, which we kind of show the sampling proportion of the red chips. And we kind of see those distributions right there, and then we can make some decisions based on that. All right. Now, again, the population distribution gives the values of the variable for all individuals in the population. The distribution of sample data shows the values of the variable for the individuals in a particular sample. And then the sampling distribution of the same proportion displays the values of p hat, which of course is the sampling proportion, from all possible samples of the same size. That's where we stop as we get going today. So just one more little tip from our friends at the AP. Terminology does matters. Never just say the distribution. Always say the distribution of blank, being careful to distinguish the distribution of the population, the distribution of sample data, and the sampling distribution of a statistic. So likewise, don't use ambiguous terms like sample distribution, which could refer to the distribution of the sample data or to the sampling distribution of a statistic. Okay, you'll lose credit on free response questions, so make sure we're real solid on our vocab. Okay, so that takes care of the first half of 7.1. Until next time, I'm Mr. Boone.